Okay, we'll do another problem. Here the pressure is equal to 3 atm. The volume is equal to 9 liters. Okay, not 9 liters. It's actually 9 liters to 3 liters. The volume is changed from 9 liters to 3 liters. The temperature is a constant during the conversion period. Okay, so we should actually find the change in pressure. Difference Okay, I'll write that once more. That's too ugly. We should find the difference in pressure. What the hell? Difference in pressure. That's the question. Okay, now as you know that the equation for pressure is force by area, right? So as the pressure increases, the volume decreases, or we can put it in as the volume increases, the pressure decreases, right? Okay, now the ideal gas equation, what was it? PV is equal to nRT, right? Okay, now as you know, N doesn't change. Even though we reduce the volume, the N doesn't change. N remains constant, right? We just shrink the container or pour it into another small container, so the number of moles remains same. What about R? There is no change in units, right? We're not actually changing the unit. I mean, once we put into another container, we're not actually converting the atm to Pascal, are we? No, that would be a foolish thing to do. So the R doesn't change. Now, and what about temperature? Do we change the temperature actually? No, we don't change the temperature. So since the nRT will be equal in the first case as well as for the second case, we can conclude that the nRT initial is equal to the nRT final. So we can also say that P1 V1 initial is equal to P2 V2, the final one, V volume. Okay, now we can also change this equation as the P1 by P2 is equal to V2 by V1, right? V2 by V1. Now we have the value of P1 and P2. I mean, we don't have P2, we have P1. Okay, let me find some space. I'll move this off, this one also. Okay, I'll move this here. Okay, we have the value of P1, right? This is P1. Okay, so 3 by P2 is equal to volume 2 by volume 1. Now what is volume 2? Volume 2 is equal to 3 liters. Am I right? So it's actually 3 by 9, right? Okay, now what is this? This is 1 by 3, right? 1 by 3. We don't have to cross multiply this or anything. We already know that this is this is P1, right? So we cross multiply into P1, not 3. So we get it as 3 P1 is equal to P2. 3 P1 is equal to P2, right? So you can actually find the theory over here. The initial pressure is low, is actually 1 by third of P2, because the volume is more. When the volume was reduced 3 times, I mean was made 1 by third, the pressure also reduced to 1 by third. So the P2 will be equal to 9, right? We actually have to find only the change. We don't have to, find the the P2. Okay, so I hope you have understood how to convert that. How to deal with such kind of problems. Okay, and I also think you understood that as the volume increases, the pressure decreases, and as the pressure increases, the volume decreases, right? I've kind of proven it mathematically. Okay, now I'm gonna give an end to problems, and I also have one more concept to explain: the STP. You might have heard of STP. Not it's actually STP, not STD. STD is sexually transmitted diseases. That's not what we're talking about. STP is standard temperature, and P is pressure always. What the hell? My handwriting is so bad. And pressure. Please do forgive me. Standard temperature and pressure. That is what we're going to learn right now. It's actually it's actually a term used to describe certain things. For example, the evaporation rate, the evaporation temperature is 100 degrees Celsius at STP. We always use such things for explaining processes like that, like evaporation, boiling, and all. We use the word STP. Now, what is the standard temperature? Standard temperature. Standard temperature is always 0 degrees Celsius, the freezing point of water. It is also equal to 273.15 Kelvin, right? Okay, now what is the standard pressure? Standard pressure, as you would have guessed, is 1 atm, not 0 atm. It's 1 atm. So how many pascals? It's actually 101.325 pascals. Sorry, 101.32 kilopascals, right? Which is 101.325 kilopascals. So I'm actually looking in my notes and writing. So I've written kilopascal. There's no need for that. 101.325 pascals. Okay, that is STP. I hope you've got what STP is. So if you have if you see a statement that the evaporation point of water is 100 degrees Celsius at STP, it just means that the standard at STP. So it just means that the pressure over there is 1 atmospheric pressure. 1 atmosphere, 1 atm. Okay. Now we'll get to problems. Problems with the STP. Okay, here's the question. See, I'm not writing, I'm just typing. Find the volume of 1 mole at STP. Quite a simple question. What is the volume of 1 mole at STP for an ideal gas? Or else we can't use the equation PV is equal to nRT, right? Okay, first of all I'll write the equation. PV is equal to nRT. PV is equal to nRT, right? Okay, what is the pressure? STP. What is standard pressure? 1 atm, right? 1 atm. Let it be 1. We don't know the volume. What is the number of moles? 1 mole, right? Therefore 1. What is R? Okay, we have atm moles, and it's actually a 100 degrees Celsius, 0 degrees Celsius, right? No, we'll actually do it in Kelvin. You know, all the problems come with Kelvin. Kelvin, how many Kelvin is 0 degrees Celsius? 273.15. We do R, so leave a blank over there. 273. Now what is the value of R when it is Kelvin, mole and ATM? Okay, I've given it in the previous lectures. I hope you have noted it down. You know, I'm not writing it again, it takes a lot of time. Let me check in my notes. ATM, meter cube. Okay, I have a problem. Okay, problem over here. So actually, when it comes to ATM, we can only calculate in liters. Okay, we'll actually calculate the volume in liters. Okay, you fine with that, right? Okay, I hope that's a yes. That's a yes. So liters, the value becomes 0.082. Right? Now what is the volume? The volume is it's actually, we don't have to consider these two ones. It's actually 0.082 into 273, right? So that's the volume. Okay, let me take my calculator. 0.082 into 273, 22.86. We'll actually do with, this is actually a big principle, so actually we'll do with 273.15. Let's see what we get when we do it. 273.15, 73.15, 22.39. Now we can write this 22.4 liters, right? Okay, now that's surprising, right? We didn't mention any specific gas, right? We just said an ideal gas. So is it actually true that if we take 1 mole of an ideal gas at standard temperature and pressure, irrespective of what kind of a gas it is, we get 22.4 liters. Now that's an interesting fact, right? Quite an interesting fact. It's actually a principle. Oops. If whatever ideal gas it may be, if we take 1 mole ideal gas at STP, we get the volume as 22.4 liters. 22.4 liters, right? Okay, now what is 22.4 liters? What is, I meant how many meter cube? It's actually 0.0224 meter cube. Now that's quite an interesting fact, right? If you take 1 mole of any ideal gas at STP, we get it as 22.4 liters. Okay, so if you're given an ideal gas and someone tells you to take 1 mole of it, what would you do? You can't actually count 6.022 into 10 raised to 23 particles, right? The Avogadro's number. You just have to take 22.4 liters. Easy. Okay, so I've run out of time. See you in the next video. Bye bye.